Hello, this is Mrs. Taylor, and I'm going to walk you through how to integrate inverse trig functions. The derivatives of inverse trig functions fall into three pairs. For antiderivatives of trig functions, you use only one member from each pair. So when we're looking at integrals, we are looking at the positive counterpart. So remember when we did inverse trig, we learned that you have arcsine, arctangent, and arcsecant, or you can say inverse sine, inverse tangent, inverse secant. And there were formulas for those derivatives. And then if you were trying to find the derivative of arc cosine, it's just the negative version of the derivative of arc sine. And it's the same for arc tangent. The negative counterpart would be arc cotangent. And for arc secant, the negative counterpart would be arc cosecant. And so when we're integrating and we have functions in these forms, 1, 2, and 3, when we integrate, our antiderivative would be an inverse trig function. And so u represents a differentiable function, which means it's composite. So you could have a function within a function, and then a is greater than 0. So a is just some constant, some number that's positive. And so if it takes one of these forms, then you are looking at an integral that will, after you take the integral, be an inverse trig function. And so these work like formulas, and that means you just have to memorize them, get some flashcards or something, and work on recognizing these three formats. Some things, some patterns to look out for: if it's square root on the bottom, it's either arc sine or arc secant. They both begin with S, so square root, sine, secant. And if you have a little extra variable or something out front, that's secant. But if there's nothing out front, that's sine. Has to be a variable, not a number. And then tangent is the one that doesn't have the square root. And then, of course, you're going to have to memorize they're all u over a, but tangent and secant have 1 over a out front, and then secant has that square root. So let's look at some examples. In our first example, we have a square root. There's no variable out front, so we're looking at an arc sine situation. And the formula, or the integral, needs to be in the form 1 over the square root of a squared minus u squared. So looking at our integrand, we need to figure out what a is and what u is. Well, I can do that by taking the square root of the constant here and the function x squared. And when I do that, the square root of 4 is 2, so that means a equals 2. And the square root of x squared is x. And of course, if we're using substitution, we have to substitute everything. So if I have du here, then I need to find the derivative of u, which is just dx in this case. So through direct substitution, 4 would become a squared, x squared would become u squared, and then dx would become du. So basically, it transforms into this formula. So all I'd have to do is plug in u and a, which is 2 and x, and I would get my antiderivative. Now the next two are going to be a little more involved. You got some chain rule and things like that thrown in there. So b is an arctangent because there's no square root on the bottom. And so we're going to find a and u the same way. Take the square root of the 2. Well, that's an irrational number, so I'm just going to write it as the square root of 2. They don't have to be perfect squares. And then u squared would be the derivative, or excuse me, the square root of 9x squared, which is 3x. So my u value is 3x. And this time, if I find du, I get the constant 3 times dx. So I have to remember when I substitute back in for dx up here, not only do I put du, but I also have that 1/3 by moving the 3 over here to this side. And so when I use substitution in this case, it would look like this, where I have the 1/3 from this constant of 3, and then 2 will become a squared, and then 9x squared would become u squared. And then that 1/3, remember, is just a constant, so I can move it to in front of the integral. And when I do that, this integral would then look exactly like this formula. So I just plug in my a, my u, and my a. And do not forget that you have a constant of 1/3. So that 1/3 goes out front. And then you have 1 over a, which is the square root of 2. And then you have arctangent u over a, 3x over the square root of 2. And of course I could simplify this. I can multiply these two fractions. And then I could rationalize the denominator here by multiplying top and bottom by square root of 2. But remember, with free response, we don't have to do that. So we're going to leave it like that just to save ourselves from any errors that will make us lose points. All right, C, the last one. There's a variable out here out front of the square root, so I know it's arcsecant. So I'm going to find my a value and my u value. A will be the square root of 9, which is 3, because remember, a is your constant. And with secant, it's backwards. It's u squared minus a squared. And then the square root of 4x squared would be 2x. So that's my u value. And if I take the derivative of that, I get 2dx. So I've got another chain rule situation here where I've got to remember that dx is equal to 1/2 du. And then the other thing that's happening here is I have this x that I have to substitute for. And so x equals, if I use this equation here, u equals 2x, x equals 1/2 u. So when I substitute in for x, not only do I have a u there, but I have a 1/2. So once I substitute, it looks like this. I have this 1/2 here from the du equals 2dx. And then I have this 1/2 u down here because of x equals 1/2 u. And then, of course, my u squared minus my a squared and my square root. And one thing I notice is that I have a 1/2 on top and a 1/2 on bottom. And so those eliminate. And once they do, this matches my setup here for this integrand perfectly. So all I have to do now is just plug in my a and my u and my a, and I'm ready to go. So 1 over a would be 1 over 3, and then the absolute value of u would be absolute value of 2x over a, which would be 3. And so that would be the antiderivative for C. And so one question you may be asking is, okay, if I have an entire sheet of integrals, how do I know to use this as opposed to our other methods? And really it's a matter of trial and error. If you use u substitution and you have u equals a function, but du doesn't exist in the integrand, and let's say you try long division to simplify, or you try to separate it into separate fractions and simplify, and nothing seems to work, then you're probably looking at an inverse trig antiderivative. And so usually it's your last resort. So trial and error through every other method we've learned, and then you'll probably land on this if nothing else works. And so that's integrating with inverse trig functions.